Von Schmohawk, and welcome to YU. When we first introduced systems of linear equations, we started by studying simple examples involving systems of two equations and two variables. We then introduced the concepts of dependent and independent systems. We showed that an independent system of two equations and two variables always has a graph consisting of two distinct lines. Those lines can intersect at a single point, giving the system a single unique solution, or the lines can be parallel, and in this case, the system will have no solutions. We also showed that if a system of two equations is dependent, it will consist of two equations that describe the same line. In this case, since the two graphs intersect at every point, the system will have infinitely many solutions. Additionally, since the two equations describe the same line, the equations must be either identical or multiples of each other. This makes it easy to tell if a system of two equations is dependent. If the equations are multiples of each other, then the system is dependent and must have infinitely many solutions. This is true of any dependent system of two equations, many solutions. This is true of any dependent system of two equations, regardless of the number of variables. However, in systems of more than two equations, there are ways that the equations can be dependent without being multiples of each other. Take, for example, this dependent system of three linear equations in three variables. No equations in this system are multiples of each other, yet they are all still dependent. So what property makes equations dependent if they're not multiples of each other? Mathematically speaking, in a group of equations, a dependent equation is a linear combination of one or more other equations in the group. So what exactly is a linear combination of equations? A linear combination of equations is produced by first multiplying each equation by a constant and then adding the results. For example, this equation is a linear combination of the two equations on the right, since if we multiply the top equation by 3 and the bottom equation by 2 and then add the results, we get the equation on the left. Since this equation was produced by multiplying the other equations by constants and then adding the results, it is a linear combination of those two equations. And adding the results, it is a linear combination of those two equations. Mathematically speaking, in a group of equations, a dependent equation is a linear combination of one or more other equations in the group. So what exactly is a linear combination of equations? A linear combination of equations is produced by first multiplying each equation by a constant and then adding the top two equations instead of multiplying the top by two. Of course, different linear combinations of those two equations could be created by choosing different multipliers. For example, instead of multiplying the top equation by 3 and the bottom equation by 2, if we multiply the top equation by 4 and the bottom equation by 1, and then add the results, we get a different equation, which is another linear combination of the same two equations. Linear combinations can be made by adding multiples of any number of equations. For instance, we could add a multiple of -1 times a third equation, producing a linear combination of 3 equations. So let's take a look at a dependent system of 3 linear equations in 2 variables. The 3 equations in this system are all dependent. Each equation can be derived by multiplying the other 2 equations by constants and then adding the results. For instance, adding 1 times the equation x equals 2 to 1 times the equation y equals 3 produces the equation x plus y equals 5. Likewise, adding 1 times the equation x plus y equals 5 to -1 times the equation y equals 3 produces the equation x equals 2. And adding 1 times the equation x plus y equals 5 to -1 times the equation x equals 2 produces the equation y equals 3. Since each one of these 3 equations is a linear combination of the other 2, since each one of these three equations is a linear combination of the other two, all three equations are dependent. Notice that even though this system is dependent, it has a single unique solution corresponding to the common intersection point of the graphs of the three equations. This shows how it is possible for a system with more than two equations to be dependent without necessarily having infinitely many solutions. Let's take a look at a few more examples. As we saw, this system of two equations is dependent, with infinitely many solutions. But let's say that this system contained a third equation, whose graph intersects the graph of the other two equations at a single point. This system is still dependent since it contains a group of two dependent equations. But now, instead of an infinite number of solutions, it has a single unique solution, since there is only one point which satisfies all the equations in the system. It is also possible for a dependent system of more than two equations to have no solutions. For example, if the graph of the third equation was parallel and distinct from the graphs of the other equations, this system would still be dependent, since it contains a group of two dependent equations. But since no solution can satisfy all the equations in In the system, it is also inconsistent, having no solutions. Likewise, dependent systems of more than two equations with three or more variables Likewise, dependent systems of more than two equations with three or more variables may or may not have infinitely many solutions. For example, this dependent system is made up of a group of three dependent equations, and the system has infinitely many solutions, represented by the intersection line of the three planes. But let's say a fourth independent equation was added, whose graph intersects the other plane's line of intersection at a single point. Then, although this system contains a group of three dependent equations and is therefore a dependent system, it has a single unique solution, since only one point exists which satisfies all the equations in the system. Likewise, if the fourth plane was distinct and parallel to one of the other planes, then this system would still be dependent but inconsistent, since no solution exists which can satisfy all the equations. So although So although dependent systems can have infinitely many solutions, it is also possible for dependent systems with more than two equations to have a single unique solution or no solutions. Saying that a system is dependent simply means that some of the equations in the system are dependent. And saying that a system is independent simply means that none of the equations in the system are dependent. So how do we know whether or not a system of equations is dependent? It is usually easy to spot when two equations in the system are multiples of each other. But it is not always easy to tell when equations are linear combinations of two or more other equations. Fortunately, the process of Gauss-Jordan elimination automatically does this work for us. In the next lecture, we will see